unit today on solutions. The test last time on the other one, for the 37 that took it, only 9 were down below 70%, which is good. Your test scores are up on your Encore, so you can look at those. I'll hand back the written part later so you can look at it, but then we'll hand it back in because we don't have those go out, but you can see what you did. Okay, today we're going to do a lecture on solutions. You should have done quiz 8.1. Assignment 8.1 is also going to be due next time, so as you have some down point during the lecture or whatever, work on that. We are going to do a little lab today on solution, suspension, and colloid. And the Fed activity we might be moving till next time. It's all right. Okay, so getting your notes out. The objectives of the lecture today are threefold. We're going to learn how to label heat curves. We're going to use them and learn how to label and use phase diagrams. These are two that are often used on ACT and SAT, so it's a good thing to be able to do. Number two, we're going to be able to describe a solution in terms of solute and solvent and solvation, not salvation, but solvation. And number three, we're going to be able to determine whether a mixture is a solution, a colloid, or a suspension. And then we're going to do a lab where we actually have to determine that. So that's what's up today. Again, assignment 8.1 is what we're doing later. This is where we start real chemistry as far as getting in and getting dirty with each type. So as you're looking at your heat curve here, these are the parts of the heat curve that you need to know. The red parts are where we are heating a phase. So the bottom one is when we're heating a solid. The middle one is when we're heating a liquid. And the last one on the right is when we're heating a gas. The flat lines are when we're changing phases, or the blue lines up there are where we're changing phases. The lower one is when we're changing from a solid to a liquid. This would also be known as melting or freezing, depending on which way you're going. The top one is when we are boiling a liquid or evaporating a liquid, or going the other way would be condensing a gas to a liquid. So we do need to know each of these parts. We're going to be putting more stuff on this graph. So has everybody got the parts down? What is it happening in each one? Not quite yet, okay? So again, anytime that you have a slope, you're going to do a temperature change. Anytime the slope is flat, we're not doing a temperature change. Just a phase change. So because of that, remember this equation, Q equals MC delta T? We've been working with that. That is when we are changing temperatures. The flat parts, we have to use a different equation because if we put delta T in there, what would happen? We'd always get 0, right? Because if we don't have a change in temperature, it would be 0. So we use what's called a heat of fusion, times it by the mass, or a heat of vaporization and times it by the mass. On the side, you had some numbers. So on the side of your notes, these numbers relate to what the C is, because at each section, the C changes. So the C for ice is different than the C for water, which is different than the C for steam. As we get to the fusion and vaporization, those also change. This 333 joules is the heat of fusion. Then we go to the heat of water, or the specific heat of water. This is something we already knew. This one goes in here. Then we get to the heat of vaporization. Notice how much bigger it is than the heat of fusion. Heat of fusion was only 333, where the heat of vaporization is 2,660. So it's a lot more energy needed to vaporize. And then the last one, the CP of steam, we get back to a little bit below what the CP for the solid was. Okay, it doesn't take quite as much energy. So we are going to be using this. Last unit we used MCP delta T a lot, but we stayed within that second red area. Okay, and we need to know that there's other areas that we're going to work with. Okay, I can go back, yes. You what?
No, I thought it was the same graph.
No, this next one is another graph that we also use. It's called a phase diagram, the one on the next page that I just flipped to for a second. This is another way to look at solid liquids and gases. Yes. Okay, so it's another way to look at solid liquids and gases. So Many of you heard of melting and freezing before, and you've heard of vaporization or condensation, in other words, boiling. But probably the newer words are used, the lower part of what we call the Y, is going from a solid to a gas. That's called sublimation. You've experienced it by having dry ice go to gas. Dry ice does not go through a liquid stage. This is carbon dioxide. Carbon dioxide at room temperature goes straight from a solid to a gas. In order to make dry ice, we take that gas, put it under a lot of pressure, and we do what's called deposition, or depositing it into a solid. So going backward and forward on this line right here tells me what I'm doing between a solid and a gas. Between a liquid and a solid, the upper part, left-hand part of the Y, melting or freezing, and the lower part of the Y is where we boil, okay? So we're going to get vaporization and condensation. A couple other points that we need to know on here are our triple point. The triple point is where all parts of the Y connect, and that is when I can actually boil ice water and get a vapor coming off, which is sort of cool, but it only happens at a specific pressure and a specific temperature. Up there at the very top, so that was a triple point right here. The other point we need to worry about is the critical point. The critical point is past that point, I can't, no matter how much pressure I put on something, the temperature is so high I cannot make it a liquid. We get what's called a supercritical fluid, that if you take a 90 degree from, go this way 90 and this way 90, this becomes a supercritical fluid, which is not very, what am I trying to say, stable. Okay, we get a supercritical fluid. So we need to know all parts of this. Now, the thing that they like you to be able to do is to be able to read the graph. So if I want the triple point and I want the pressure and the temperature of the critical point, I need to be able to read it. If I want the, or sorry, that's a triple point. The critical point's over here, so I need to be able to read it this way. I need to be able to read the graph. I need to be able to, given a certain temperature and pressure, be able to tell me what phase is it in, or is it changing phase? Is it at equilibrium between a solid and gas, or liquid and solid? Okay, we're going to add to this graph a little bit more. Has everybody got this part down? It's a lot of stuff to write on, I know. Okay, so we also have what's called normal. And normal is where I go across the graph at 1 atmosphere. And it's really important. It's the same graph, guys, same graph. I'm going across right at 1 atmosphere. Where that 1 atmosphere hits right here and right here, this becomes my normal freezing point, or it can be called normal melting point, depending on which way I'm going. And I should be able to grab what temperature that is. Normal melting point or freezing point. This point right here is known as my normal boiling point. Boiling point. And again, I should be able to determine what that normal boiling point is by coming straight down. Okay? It's either normal freezing or normal melting point, depending on which way you're going. Okay? Usually we don't have a normal condensation point, but it could be called that too for the boiling point. And this is an English version of the spelling, so atmosphere is a little bit weird, and vapor and temperature are a little bit weird. Well, temperature's right? Just looks weird from the angle I'm at. Okay, so we already talked about the supercritical fluid. I already labeled that for you up there in the far corner so you know. Again, this is points that you should know on any phase diagram. Okay, now we're going to actually take in the next slide and we're going to practice. So you don't have these on yours, but we're going to practice. So, and the thing didn't cover very well. So at what pressure and what, let's do this first. Where's my solids?
On the left.
On the left of the Y, good. Where is my gas? Where it says vapor, okay, gas. And where's my liquid?
Middle.
In the middle, that's pretty easy. Okay, where is my critical point? Top right Y, yep. This is my critical point. So from between my critical point, I can find, and I didn't draw a very great straight line there, I can find the pressure, which would be about what? This is a little bit weird graph to look at. About 300. Okay, what would my temperature be? About 625, yes, somewhere in there. Okay, what about my triple point? Middle of the Y. Okay, so coming across and coming down, where am I at? 290 and 0.009, 0.008, something like that. Okay, now, what is it when I go this way across that line?
Melting.
No.
No, freezing.
No.
Boiling.
Sublimation.
Oh.
Remember, this is the funky one down here. What if I go this way during that line? Deposition, good. Okay, now what if I go this way on that line?
Evaporation.
Evaporation, or also known as boiling point, right? What if I go this way? Condensation, good. And what if I go this way?
Freezing.
Freezing, good. And if I go the other way?
Melting.
Okay. Other way, yep. Change the arrow, thank you. Melting. Okay, I think I've got one more graph, so let's see. Okay, so we also need to be able to say, if they give me a starting point, what's going to happen if I increase the pressure, decrease the pressure, if I increase the temperature, or decrease the temperature. So what happens if I'm right here, the point they gave me, and I say the temperature is going to increase? Tell me what's going to happen. It's going to go this way, but what's going to happen? Well, when I hit this line at this temperature, it's going to melt, right? And if I keep going, then I'll turn to a liquid, and then at this point, I will, at this temperature, what? Vaporize. And then past that point, I'm just a gas, right? What happens if they said increase the pressure? If I, from that point right there, if I increase the pressure, what's going to happen? Stay solid. What if I decrease the pressure? Right here, at this point, at this pressure, and at this temperature, I'm going to come a gas. Okay? So you need to be able to read the graph and be able to tell me what's going to happen. Okay? Using the correct words. Does that make sense? Okay. Going forward. Now we're going to go into your next page, which is talking about heterogeneous mixtures. So and these are going to go back and forth on this page. I'll give you more, and then you can go back and fill in more up and down. So as we look at solutions and heterogeneous mixtures, a solution is homogeneous throughout, meaning the same throughout. Doesn't change. A heterogeneous will settle out. So if I have chocolate milk, I love chocolate milk, you put that couple scoops of chocolate in, you stir it in your milk, and then if you wait too long, all the chocolate goes to the bottom. Right? Then you got to stir it up again, then you drink it fast, or stir it, drink it, whatever. When things separate out, you're going to have a suspension. Okay? You're going to have a suspension. So heterogeneous mixtures are suspensions. We also have some other words that we need to work with. So heterogeneous mixture is different throughout, and it is a suspension. Concentrated versus dilute. Concentrated, you're going to have a lot of stuff in a little bit of liquid. Dilute, you're going to have a little bit of stuff in a lot of liquid. So what's this stuff called? A solute, it's what is being dissolved, and a solvent is what is doing the dissolving. So a solute is what's being dissolved, and a solvent is the thing that's doing the dissolving. When a solute and a solvent come together, we call it solvation. Not salvation, solvation. The process of solvation produces a solution. Okay? So going forward here, we'll hit all this. Now, to have a true solution, I have got to have a particle less than 10 to the minus 7 centimeters big. We talked about suspension here. A suspension has to be greater than 10 to the minus 5th. Well, we have this point in between here and here. These are what is known as colloids. So they're the in-between, the go-between. These particles in both the colloid and the suspension are big enough that they can catch light and scatter light. Okay, so we're going to be using light to figure out, do I have a solution, a true solution, or do I have a colloid? Suspension we'll be able to tell because what did I tell you about suspension? It's a heterogeneous, and after you let it sit for a minute, what happens? Sinks to the bottom. So I'll be able to tell a suspension. But the colloid, it'll look like a solution until I shine light through it. Okay? So we're going to go forward. Everybody okay with sizes and got the sizes down and what's what? Okay, give you a few seconds more. Homogeneous would be both a true solution and a colloid. So homogeneous is the same throughout. Yes? We're going to go into that. So both colloid and suspension will reflect light. Heterogeneous would be your suspension. So heterogeneous means different throughout. Okay, we okay to go forward? Everybody got a definition down? Because we are going to be using them in lab. The numbers that are what? So a colloid is between this and this. Bigger than that is a suspension, smaller than that is a solution. Now you'll notice that both of these say 10 to the minus 7. So this part right here and this point right here are sort of the fuzzy dividing lines. They're not a crisp divide. Okay? All right, so let me give you some examples of colloids. You don't have this down in your notes, but I'm going to give you some examples that we have as colloids. Fog. So if you've ever gone out on a morning in the winter and there's fog outside and you get in your car and you go to drive to school and you turn on your headlights, what happens? Everything lights up, right? You don't see right in front of you because the whole area lights up. That's what's called a Tyndall effect. That's the reflecting of light. So aerosol spells will do that. Smoke can be a colloid or it can actually be a suspension. If I have a house fire, I get some big particles. Those big particles are going to be suspension. The smaller particles will make it smoke. Airborne germs are also a colloid. Whipped cream and suds, milk and mayonnaise, paint, you can just go down through. Notice the dispersing medium. This would be my solvent. And my dispersed substance, this would be my solute, making my solution. Does not have to be liquid-liquid. Okay, so don't get that out of your head. It can be a gas and a liquid. It can be a gas and a solid. It can be all those that we've got right there form colloids. Okay, so it's a very broad area. There's actually a study on colloids. There's a chemistry with colloids. Marshmallows, yep. So here's a shorter version. You can sort of just see the difference between them. Air, as long as it's not our winter inversion, thank you, air, then it's a solution. But if it's our inversion, the light will shine through and do the Tyndall effect, and we'll talk about that in the next one. And that would move it to a colloid. So we've got several different things that we can sort of look at here. So again, a definition if you missed the first ones. Suspension and colloids are not considered solutions, they're considered mixtures. Okay, so suspension and colloids are not considered solutions, they're considered mixtures. A suspension is when the particles are so long, they settle out. A colloid, the particles are in between a suspension and a solution, and they stay in solution. They don't fall out. Okay? All right, so this is what we call the Tyndall effect. The Tyndall effect is a scattering of light. So the fog in the headlights kind of thing going on here. If we take a flashlight and we shoot it through a solution in a colloid, before we shot the light through, they would look the same. But as we shoot the light through, we can actually follow the pathway of the light through a colloid that we can't do during a solution. Now you've got to be careful, and I put this picture up because it looks like the light's coming through, but right here it's just the glass, because it's bent, is bending the light. There's no pathway through. On this one, you can see the pathway, and it's also lighting up around it. That's a Tyndall effect. if you're in the woods and you come through and you can actually see the pathways of the light, that's a Tyndall effect. You've got a lot of particles in the air that are big enough to reflect light. If you see one like this, it's probably the water particles in the air that are reflecting the light. Okay? So this is a Tyndall solution. So on your picture, on your paper, you have this picture. Now, remember that you can see light coming in here and here on a solution, but it's usually just the bottle. Okay? A colloid, you'll see the light coming through, but you'll also see the rest of it sort of light up. Same thing with a suspension. So how can I tell the difference between a colloid and a suspension? Leave the suspension there and it will separate, or it will have particles big enough you can see it. Good. What's this? What is this and this called? What effect is this called? Tyndall. The Tyndall effect. And that's where it reflects light. Guy that figured it out, yep. Okay, reflects or diverts light. Scatters light is what I was looking for. Okay, so then we go back to how do I make up a solution? So a solution is made of a solid, what's being dissolved, a solvent, what's doing the dissolving, and you get a solution through the process of, what was it? What was that process called? Solvation. Not salvation, but solvation. Okay? So, solid, solvent, we get a solution through solvation. Okay, again, to remind you really quickly, a solid is what's being dissolved, a solvent is what's being dissolved in, or what is doing the dissolving. And why are chemists great at solving problems? Because we have all the solutions. Haha. We do everything in solutions. So if you're making sweet tea, the tea and the sugar would be the solute, and the water would be the solvent. Okay? So that would give you sweet tea. So how does solvation work? When something solvates, this would represent a sodium chloride crystal. And it's put in water, and the water is, the red is the oxygen, the white is the hydrogen. In this next picture right here, you can see on this one the green, and it's surrounded by white hydrogens. Well, white hydrogens have a slightly positive charge, right? So this Cl, this would have to be a Cl minus because it would be attracting the hydrogens. If we look at this other one right here, we have the oxygens next to it, so this would be the Na plus. And what they do is they just surround each molecule with water. And the water, depending on if the molecule or the ion is positive, then the oxygens will surround from the water. And if the thing is negative, then the hydrogens will. That's what is known as solvation. Now, how do I tell the difference between solvation and an actual reaction? Can I help you? Yep. Okay, so how do I tell the difference? So students beware. We could have a reaction going on. Okay? It is a physical. So if I start with two different things and I put them together and then I evaporate off one and I end up with something new, that's a chemical reaction. No, I think it's copper chloride. So they've taken some metal and they've put it in hydrochloric acid and they got out something new. That's a reaction. If I take something, I put it in like salt and water, and then I evaporate off the water, I'm going to get the salt back. That's solvation. So if I get something new, it is a chemical reaction. If it doesn't change, and by evaporating off the solvent, I get back what I had, then that's solvation. Okay? So I want you to talk to your partner real quick. I'm going to take some views. I want you to come up with a true solution and be able to tell me what the solid is and what the solvent is. And if somebody else has something else, you have to come up with something else quick. Improv. So, okay, wait. You got to go. You got to go with 30 seconds. Okay, here we go. I'm going to do the quiet. Give me an example of a solution, true solution. Oh, okay. True solution. That would be a suspension. Okay, yes. Brass is a colloid. No, it's a solution. It's a solution, you're right. Two metals together, it is a solution. Okay, yes. Air is a solution. Okay, what else? Yes. In the bath it would be. In the bath. So what would be your solid and what would be your solvent?
So solid would be like bath salt, the salt would be water.
Right, good.
Sweet tea. Sweet tea.
Sweet tea. Okay, what is your solvents? What's your solvent?
Solvent. Solvent.
Solvent.
Solvent. Tea. The tea. No, that'd be the water.
Water. What is your solutes?
The sugar. Sweet.
And tea. Okay, need another couple examples. Who's got them? Yes. 1, 2, 3. Okay. Good morning, Stockton. Yes, you can do another one. Okay, let's come. Coffee, yes, coffee would be. Okay, so going forward, if we form a solid, okay, we form what's called a precipitate. We've actually worked with precipitates before when we were first learning how to do double displacement. I don't know if you remember the lab we did back in the back, where you had to decide if we were going to get precipitate or not. Okay, so over here on this little thing right here, you've got this diagram on yours. So the first one is a solution. The second one would be a suspension, but after time, the suspension would separate. The bottom part is what we call a precipitate. The top part is what we call a supernate. So you need to write down those definitions. Yeah, the supernate is what's on top, and if you let a suspension settle, oftentimes the supernate will not give a Tyndall effect. It's on your paper. It has lines that you're going to write stuff down on.
Okay.
Precipitate. The bottom right there, so you got a suspension and a precipitate on the bottom. Okay, going forward. Okay, we have soluble and insoluble. So if something is soluble, tell me what happens. It will dissolve. If something's insoluble, it won't dissolve, right? Like a hand, hopefully won't dissolve in water. It will dissolve in hydrochloric acid, though. Okay, so some examples, salt and water would be a soluble substance. Oil and water would not be insoluble. But in chemistry, we don't use just soluble and insoluble. We use what's called miscible and immiscible. So difference is miscible, I think mixable. It will mix. It's soluble. Immiscible won't mix. It's insoluble. Okay? Different words for the same stuff. Usually miscible has to do with two liquids. Okay? Usually miscible has to do with two liquids. So miscible would be like soluble, and immiscible would be like not soluble.
So you'll miss it once you mix it in.
Okay, going forward. So if you need to make a solution, Kool-Aid would be like making a solution. We'll do a Kool-Aid lab later. So the solid would be the sugar and the Kool-Aid mix. The solvent would be the water. So we would be able to get a solution, hopefully. So we're going to go on and do a suspension lab real quickly. Doesn't look like the other classes there, so we're going to beat them out this time. So what we're going to do is we're going to go back in the back. You will need glasses on. You will need to really quickly mix up your solutions. I will give you about 4 minutes to do that, at which time I'm going to turn off the light. Then we're going to try to see if we get the Tyndall effect. And I'll turn on the light. You need to finish and then come back in. We'll get stamps for those that watch it. So let's go. On your